will talk about in this module about the approximation methods in quantum mechanics. We earlier talked about the applying Schrodinger wave equation to simple molecular systems, simple atoms like hydrogen atom, and some model systems like particle in a one-dimensional box, three-dimensional box, simple harmonic oscillator, rigid rotor, and some variations of particle in a one-dimensional box also we did. Okay. In fact, two-dimensional box also we did, but it's all variations of the same problem. Okay. Some problem over there. Okay, in this module, we will talk about approximation methods in quantum mechanics. In the earlier modules, we have talked about the postulates of quantum mechanics, and then we applied Schrodinger wave equation to simple system like particle in a one-dimensional box, three-dimensional box, hydrogen atoms, rigid rotor, simple harmonic oscillator, etc. In all these calculations, what we have seen is that when we apply Schrodinger wave equation, we get the eigenvalue and the eigenfunctions, and then we normalize the eigenfunctions, and we also interpret the those eigenfunctions in terms of electron density plot and all the radial distribution functions and everything we talked about. In case of hydrogen atom, we have seen the angular dependence of the wave function also, the angular part of the wave functions together, we call it spherical harmonics. That is theta and phi part of the wave functions together are called spherical harmonics. So we plotted these graphs and we have interpreted it for 1s, 2s, 3s, 2p orbitals, all we have done it. Okay. So what I mean to say that for all these smaller systems, we were able to apply Schrodinger wave equation and get the exact wave functions. But the moment you go beyond hydrogen atom, you talk about a helium atom, you talk about H2 plus molecule ion, you talk about H2 molecule, simple systems. But since there are many particles involved, more than one nucleus is involved, more than one electron is involved, so hydrogen solution of the Schrodinger wave equation becomes impossible. We cannot get the exact solution of Schrodinger wave equations. And the reason for this is that there are many repulsive terms which gets included into the potential energy function. So if you look at the helium atom, in helium atom you have one nucleus where you have two charges, two protons is there, and you have two electrons, one electron here and an electron here. So what happens? These electrons are attracted by this nucleus, both electron 1 and electron 2 is attracted by the nucleus, and there is an inter-electronic repulsion in between the two electrons. The opposite is that if you talk about H2 plus molecule ion, this H2 plus molecule ion, then here you have two nucleus, N1 and N2, and one electron. So both these nucleus will attract electron will be attracted by N1 also, and electron will be attracted by N2 also, but there will be internuclear repulsion R. Okay. And because of this, what happens? That the potential energy term of the Schrodinger wave equation becomes more complicated. This term, potential energy term, here 2E square divided by R, 2E because you have two protons at the nucleus, okay, and we suppose E to be the unit charge which is present on the electron and the proton, then we can write in a very simple way. So the negative sign is minus 2E square by R1 minus 2E square by R2 is negative. So these are attractive interaction. The distance is also given R1 and R2. So the attraction between electron 1 and nucleus is given as minus 2E square by R1. Attraction between electron 1, 2 and the nucleus is given as minus 2E square by R2, and the inter-electronic repulsion is given as plus 2E square divided by R. So this is the inter-electronic repulsion. Inter-electronic repulsion. Okay. And this is 1 by 4 pi epsilon is permittivity constant. If you look for H2 plus molecule ion, then again you have two attractive terms, which is between electron and the nucleus 1 and electron and the nucleus 2. So the first term is attractive term, the second term is also attractive term, but the third term is the internuclear repulsion, and this is E square by R. Okay. So these potential energy terms complicate the Schrodinger wave equation so much so that we are unable to solve this equation. Another issue Hamiltonian of helium atom is that in helium atom you have two nucleus and one electron. Okay, so in fact the if we what is written here is this is the kinetic energy term. This the first term in the Hamiltonian, minus h cross square divided by 2m. You already know this, del square is the kinetic energy term, and thereafter you have potential energy term V, which is given as V. So if you write this for the helium atom, then you write minus h cross square divided by 2me del 1 square plus del 2 square. Actually, I should have written here three terms because you have the 1 and 2 are the nucleus, and for electron we should write, sorry, I should have added this one, del E square also. Okay, and then the potential energy terms will be, which is written on the previous slides, is minus 2 E square divided by R1, minus 2 E square divided by R2, and minus 2 E square divided by capital R. So plus 2 E square divided by capital R. So this is your internuclear repulsion, because we are talking about helium atom where you have two nucleus and one electron. Okay, now so this becomes the Hamiltonian. Hamiltonian becomes so number of kinetic energy term will depend upon the number of particle which is present. We have three particles, two nucleus and one electron, so it will be 1 square and 2 square. So see, the kinetic energy terms is this one. The general for multi-electronic atoms, a general Hamiltonian will be this one, where you have kinetic energy term, where you have potential energy terms, and where you have potential energy attraction and potential energy repulsion, both repulsive term also. Okay, so whatever be the number of particles from I to n, you will write del I square. That is the kinetic energy term, minus h cross square divided by 2m into del I square. So for each nucleus and for each electron, you will have to write this kinetic energy term, and then you will analyze that what kind of interaction is taking place in the system, and depending upon attractive and repulsive term, you will write the second and third part, Coulombic attraction and Coulombic repulsion. So your Hamiltonian becomes big. There are many terms in the Hamiltonian, and this, because of this inter-electronic repulsions and nuclear repulsions, it is very difficult to solve the Schrodinger. Not only difficult, it's almost impossible. It's impossible to solve the Schrodinger wave equation for such system, helium atom, H2 plus molecule, and H2 molecule, and so and so. Okay. But one consolation is this, that if you have many nucleus and many electron, then nucleus being very heavy, we suppose it to be a static, and we neglect all the kinetic energy terms related to magnetic. So within the Hamiltonian, what you can do is you can write the Hamiltonian, the kinetic energy terms of the Hamiltonian we can neglect. So when you write the Hamiltonian for a system which is a helium atom or other atoms, then what we do is that we neglect all the kinetic energy terms related to nucleus, because nucleus being heavy, it is supposed to be static. Okay, and the one of course this is an approximation, and this approximation is called Born-Oppenheimer's approximation. So when you have a multi-electron atoms, a general Hamiltonian will be like minus h cross square divided by 2me, then del I square will be written for all particles which is present from I to n. Okay, because this will denote the kinetic energy, and then after this, what you will write is all the attractive terms and all the repulsive terms. Attractive terms will have a minus sign for the potential energy, or minus sign, and repulsive term will have a positive sign. But when we talk about the multi-electron atoms, then nucleus are very heavy, and if the nucleus are heavy, then they are supposed to be constant, to be static. They are not moving, and we can do this approximation, and we can write the kinetic energy term for electrons only. That's called Born-Oppenheimer's approximation, and then further calculations can be made depending upon from this particular Hamiltonian. Okay, so Born-Oppenheimer's approximation facilitates the thing that only the kinetic energy term will involve only electrons only, and no nucleus. Nucleus we can neglect, or we can suppose it to be frozen and electrons to be moving in the field of nuclear charges. That is the idea of Born-Oppenheimer's approximation. Okay, but even with that approximation, it becomes very difficult to solve Schrodinger wave equation for multi-electron atoms or for even for the small molecules. Okay, because the potential energy terms becomes very complicated, and this complicates this. So any analytical solution and any actual solution of the Schrodinger wave equation becomes impossible because of the repulsive term. I said you interelectronic repulsive term. So does it means that the road ends here? No. In quantum mechanics, there are ways to find out the eigenfunctions and eigenvalue for such systems where the analytical solution of Schrodinger wave equation is not possible. For such system, what we use approximation methods. Okay, and we say that okay, fine, if we can't get the actual value or exact value of the eigenfunctions of the eigenvalue, then we must calculate the value which is very near to the actual value, and then we say that's what is approximation. If you can't get the exact, then very near to the exact you get. Okay, so these methods are called approximation methods. So remember that approximation methods are used because there are cases where analytical solution of Schrodinger wave equation is not feasible, and you cannot get the exact eigenfunction or exact eigenvalue. Normally what we did is we have talked about the hydrogen atom, and we have talked about the energy of the hydrogen atoms, and I said you that it is the ground state energy minus 13.6 electron volt we got in the hydrogen atom solution, which you were already aware of in case of Bohr's model also. Okay, so the ground state energy is the minimum energy state, and if you cannot get the ground state energy, if you cannot get the exact solution, you cannot get the ground state energy, then try to reach as close as possible to the ground state energy and as close as possible to the ground state eigenfunction. That's what is the goal of approximation methods. And two broad methods which is used in approximation method is variation method and perturbation method. So the first thing is why it is needed and how it is done. So why it is needed we did, because it is needed because of the inter-electronic repulsion or internuclear repulsion terms, potential energy terms becomes big, very large, and these terms complicate the Schrodinger wave equation and make it infeasible, and it is not feasible to solve the Schrodinger wave equation. So we require an approximation, and once we require we require the approximation. Now, what is the methodology used for this approximation? Then there are two broad methods. One is called variation method, and another is called perturbation method. We will do both these methods separately, and we will do many examples of these variation methods in this module and the module thereafter also. Okay, so how it is done actually? The one thing is clear that we have a system which is complicated. We do not have the analytical solution for the Schrodinger wave equation, and we need to approximate eigenfunctions and eigenvalue. Okay, and in variation method, what we do, what is the methodology is that the first thing which we do is that we guess a trial function. Okay, the initial step is to guess a trial function, and then the fundamental principle of fundamental premise is that the energy corresponding to the trial function is always greater than the actual energy of the system, because we don't know the eigenfunction, and if you don't know the eigenfunction, then whatever eigenfunction you guess is not the actual wave function, and if it is not an actual wave function, then energy corresponding to this particular wave function will always be greater than the ground state. So the basic principle is that any trial function which you guess, and if you find out the energy corresponding to this one, it will be greater than the ground state energy. Okay, so energy corresponding to trial function is always greater than the actual energy of the system. Then why we are guessing it? Why we are guessing it? Because from here we will start and we will try to reach the energy very close to the ground state energy, because we don't have the actual thing, so we don't have the minimum thing. Actual is the minimum ground state energy, but minimum we don't have, so whatever you guess gives you an energy higher than the ground state energy. Okay, now you see that if you are guessing a wave function, and you are guessing multiple wave functions, then out of the multiple wave functions, the one which is giving the lowest energy is the best trial function. Okay, the lower the energy, the better is the corresponding wave functions. Okay, so if you are guessing wave function psi 1, psi 2, psi 3, psi 4, psi 1, and you find out energy of these E1, E2, E3, E4, and then you see that E3 gives the minimum energy, then the guessed trial E3 is the best trial function which you have used. Okay, so that way you can understand. The lower the energy, the better is the corresponding wave functions. Now, once you have guessed that okay, psi 3 is the best wave function and E3 is the minimum energy, then you will have to find out that is there a way to improve this also, and if there is a way, we will improve that function, and again we will do for psi 3 prime, psi 4 prime, so that again the energy decreases further. That is what is the principle or the philosophy of variation methods, that you guess a trial function, find out the energy corresponding to it, and see when you are getting the minimum energy. The minimum possible energy which you get from the trial wave function is always greater than the ground state energy. Okay, and whatever improvement you can make, you make the improvement to the guess trial function, and you reach the as minimum as possible energy value, and then the corresponding trial function is called the best trial function or best eigenfunction for the system. Now, how to find out this energy of the system? Then we use the quantum mechanical postulate. The expectation value of the of any physical variables can be found from quantum mechanical postulate by a Rayleigh ratio, which is this one. Phi integral. This integral is wrong. This integral should be here. Okay, so remove this one. This integral of phi a star h phi a d tau, and then integral of phi a star phi a d tau. Okay, so you remove this integral and add integral here. Of course, minus infinity to plus infinity I have written. Now, if your phi a is a trial function, then if phi a is a trial function, which I have written earlier, phi a is the trial function, so this energy is always greater than the ground state energy. Whatever energy you obtain here, EA is always greater than the ground state energy, E naught. Okay. Now, how to improve this wave function? If you are not getting that energy near to the ground state, then how to improve this trial function? So what we say that instead of guessing a trial function like phi a, we guess a trial function which has some coefficients. Okay, so we say that phi the guessed wave function is phi is equal to minus exponential minus lambda x. Okay, where this lambda is called variation parameter. Okay, so if it is a variation parameter, then if the guess wave function is phi is equal to exponential minus lambda x, then you can write phi is equal to if the lambda is equal to 1, your trial function will be exponential minus x. If lambda is equal to 2, your trial function will be minus 2x. If your variation parameter is 3, then trial function will be exponential minus 3x, and so on. So what we introduce, we guess a trial function which is a function of variation parameter. Okay, so you can guess a trial function like this one, and if you guess it like this one, then the value of the lambda can change, because it is a parameter which will decide that what will be the value of your trial function. So finding out the value of lambda, what you can do is that you differentiate this. You find out the energy corresponding to this one. Phi is a function of lambda. Phi is the function of lambda. So if you differentiate, if you find an energy corresponding to this one, E corresponding to phi, then this also is a function of lambda. So for finding out the lambda value, what you do is that you differentiate this energy E phi with lambda and equate it to 0. So what you are doing, you are minimizing the function. Okay, and if you, from this equation you find out the value of lambda value, and once you put this value, whatever value you put, say I'm writing lambda double prime. If you get lambda double prime here, then you your trial function will be, best trial function will be lambda double prime into phi. This is what is the logic behind variation method, that you guess a trial function, corresponding to this you get the energy, and this energy is also a function of the variation parameter. So you equate it, you take the first differential, equate it to 0 and find out the value of lambda, variation parameter. Okay, and once you equate it to 0, you get the value of variation parameter. Okay, and this variation parameter is introduced into the eigenfunction equation, and that is the best trial function. Okay, because you have got the minimum energy, you have minimized the energy. So that is how we start from the trial function, and then we calculate the energy, and then we calculate the variation parameter, and we get the eigenfunction back. Okay, so this is all about the principle of the variation method. In variation method we do this only, but the question is how to guess a trial function. Is it simply any mathematical function can be a function of the system? No, all functions cannot be. And for guessing a trial function, all the solutions which we have done, right from particle in a one-dimensional box, two-dimensional box, three-dimensional box, simple harmonic oscillator, rigid rotor, hydrogen atom, all these should be with you. Then only you can guess a trial function. Suppose you have a problem, it's for hydrogen atom, you have a problem for particle in a one-dimensional box. Okay, and what we have done? We have done that in a particle in a one-dimensional box, you have a system where if I write at x is equal to 0, if the dimension of the box is x to a, 0 to a, then we write x is equal to 0 to a, and at x is equal to 0, the wave function is 0, that you know, and at x is equal to a also the function is 0. So this you know this system, and once you know this system, then what you can do? You can guess a trial function which fulfills this particular boundary condition. Okay, you know what is the actual wave function? The actual wave function, normalized wave function, is psi is equal to root 2 by a sine n pi x upon a. Okay, so if I write x is equal to 0, okay, then sine 0 will be 0 and the function will be 0. And if I write x is equal to a, then a and a will go, and you have sine n pi, that will be 0, so the function will be 0. So this actual wave functions which you get from the particle in a one-dimensional box satisfies the boundary condition. So for guessing a trial function, you will have to write a function which is very similar to this one, that which should satisfy the boundary condition. So if I guess a trial function, psi trial, for particle in a one-dimensional box as x into a minus x, then will it fulfill the boundary condition? Yes. If x is equal to 0, psi trial will be 0. Sorry. X is equal to 0, psi trial will be 0. And if x is equal to a, then also psi trial will be 0. So though we don't know the actual wave, we know for this system the actual wave functions, but we can have a trial function like this also. X is equal to x multiplied by, within bracket, a minus x. Because if you put x is equal to a minus a will be 0 and the function will be 0. If you put here x is equal to 0, then also the function will be 0. So one of the trial function. Now, what do you expect? What should be the eigenvalue for this trial function? What should be the eigenvalue of this trial function? The eigenvalue of this trial function, you know already, is n square h square divided by a times a square for the En state, nth state of the nth quantum state. But will this trial function give you the same energy? No, it will not give, because it is not the actual solution of the Schrodinger wave equation. So with this trial function, whatever energy you get will be greater than than this energy, n square h square divided by a times a square. So that is the thing which you have to understand in variation method. That in variation method you guess a trial function and you treat the trial function through the Rayleigh ratio, and you find the energy value. That energy value is always greater than the ground state energy. Now suppose I write another function, another trial function, I write x into a minus x square. Yeah, this was psi. This is also psi trial prime. Will this fulfill the boundary condition? Yes, of course, but for the same reason, this will also fulfill the boundary condition. Okay. Will it give you the same eigenvalue? No, it will not give you the same eigenvalue as x is equal to a minus x. It will give you something else. Now I write a third wave function. Psi trial double prime x square a minus x square. Okay. So will it give the same value? No. I am guessing another trial function. X square a square minus x square. This was a minus x whole square. Now I am writing a square minus x square. So all these first, second, third, fourth, all these fulfill the boundary condition of particle in one-dimensional bound, and all these could be guessed as a trial function. Okay, and we can calculate the energy corresponding to these trial functions, and we can see which of these out of four is a good wave function or is a better wave function. Which will be the better wave function? One which will give you energy more closer to the ground state energy, that is n square h square divided by 8mv square. So that principle lies there, that for any trial function which you guess, the energy which you get is always greater than the ground state energy. Okay, and the best wave function is the one for which best trial wave function is the one for which the energy which you get is more closer to the ground state energy. Okay, this is what is the concept. This is what is the principle of addition methods. Now, if you have to guess a trial function for hydrogen atom, so what you have seen, in hydrogen atom the electron is in 1s orbital, and 1s orbital wave function we do have with us. Okay, and which tells you that the wave function is the 1s wave for psi 100. If you look at the previous modules, you will find the value. It will have a constant value, and then it will have exponential minus r divided by a naught. This was psi 100. Okay. So the solution of the hydrogen atom is known. We know the actual solution of the Schrodinger wave equation, and we know the value of psi 1s orbital. For 1s orbital, because in hydrogen atom you have 1s orbital, and the psi which is called 100 means n is equal to 1, L is equal to 0, m is equal to 0, 1s orbital. So it will have a constant multiplied by exponential minus r divided by a naught. So instead of 1 divided by a naught, if I write a wave function, a trial function as phi is equal to exponential minus cr, then this will be a trial function. C we do know, C is the variation parameter. Okay, and this trial function again fulfills the boundary condition that at origin r is equal to 0. Okay, what will be the function? Function will be 1, and at infinity r is equal to infinity, the function will be 0. So this is what is this wave function is very similar to the actual wave functions which we obtain from the Schrodinger wave equation. So now phi, if known, then complex conjugate, we do not have an I value, so complex conjugate will be same, exponential minus cr, these are real functions, and the Hamiltonian for hydrogen atom is minus h cross square divided by 2 mu square del square plus v, that you know, and then in hydrogen atom you have the potential energy minus c square by r, that you know. So Hamiltonian you can write. Now del square is the Laplacian operator and can be given by expression 1 by r square del by del r square del by del r. Now you know that this del square has del square psi is written as 1 by r square del by del r square del psi by del r plus 1 by r square, just to refresh your memory, sin theta del by del theta sin theta del psi by del theta plus 1 by r square sine square theta del square psi by del phi square. If you remember, the first part was having only one variable r, the second part was having two variables r theta, and the third part was having r theta and phi, all the three variables. Okay. Out of these, what we say that energy, we have to, in variation method, what we are concerned with, calculating the eigenvalue, and the energy of the electron does not depends on the theta and phi function. It depends on the distance from the nucleus, that is r function, r variable. Okay. So we do not write theta and phi part, we write only r part, 1 by r square del by del r square del by del r. Energy depends only upon the value of radius r and is independent of theta and phi, so it can be neglected. Angular part we neglect. Okay. So we have the Hamiltonian, of the hydrogen atom, and we have the Laplacian operator also. So we can combine these together to give you the eigenvalue equation. Eigenvalue equation is H phi is equal to E phi. So what you can write? Minus H cross square divided by 2 mu del square minus E square by R phi is equal to E phi, and minus H cross square divided by 2 mu del square phi minus E square by R phi is equal to E phi. First we will try to calculate del square phi. Okay. What is the value of del square phi? Del square phi is what? 1 by r square del by del r square del by del r into phi, and phi is equal to exponential minus CR. Okay. So simple differentiation you require to do, 1 by r square d by dr r square d by dr exponential minus CR. Okay. And then you do the differentiation. What do you get? R square will remain there, then exponential minus CR. Then you do the second differentiation, and now you have two different functions, r square and exponential minus CR. So it will be 2r exponential minus CR, and then you have minus CR square exponential minus CR. Okay. So this you get, and if you bring this exponential minus CR outside, then you have 2r minus CR square as the within the bracket. And so what you can do is that if you multiply with this r square, then you have minus 2c divided by r, and minus plus c square. Okay. So this you get minus 2c by r plus c square, and you rearrange this, what you get is del square phi is equal to exponential minus CR into c square minus 2c divided by r. Okay. Now this part we have already calculated. In the Hamiltonian, this part is known to you. So with this part you can write the H phi is equal to this one. Okay. So for the time being, I stop this module here, and you practice this and see whether you get this function or not. I said you all these calculations required your practice, so always sit with a piece of pen and paper. Okay. Now from here onwards we will continue in the next module, and we will do the further derivation, because these derivations are lengthy, so I will have to stop here and we will continue in the next module. Okay. Thank you.